Right, we can start now. So what we did yesterday, we discussed the functions. We discussed functions. Now we defined what function is and how functions act. And so far, we looked at few examples, very well-known examples of functions like the parabola, the line, and all those things. We are going to use those functions a lot just to illustrate what generally happens with the functions altogether and the class of functions. So I think people recap, they know that we said a function will always occur between two sets. Like, for example, you've got there, what am I trying to say here? I'm saying, first of all, when we talk about a function, we agreed that a function acts between two sets. In other words, here, if I say there's a function here from x to y, so I would denote that function with an f there, and then what we're sitting here actually are elements of this set. This is a set, and all that we discuss what the set is, x, and the elements of this set here are the y's. So what will happen actually, this function will assign a value y to a value x. So in such a way that if you give an x here, we must have a unique y, which we call is the value of the function at x. Is that right? We said that. So then, in this case, x and y have got names. We said x in this case would be the domain of the function. Obviously, if we deal with real numbers like we saw yesterday, we need to check very clearly what is the domain of the function. Let's say domain of the function. This is not very clear. You get that. That's the domain of the function. And then y is normally going to call the code domain. But be careful here. The code domain. What do I mean here? When I'm looking at the values of y there, I'm not trying to suggest that all the values of y are value as what are can be assigned something from x. No, I'm not saying that. What actually happens now? We're going to have something which we call the range of f. You remember yesterday we used this as the range of f, which is the set of those y's such that there is an x here, so that you can get this kind of relationship altogether. So now, when we say this function moves from x to y, we're not saying that everything in y is a value of some point in the x. No, we're not saying that. So the values which are going to have, like they say this, the range of f will be the y's such that there is, let's say there is x in capital letter X, such that y is equals to f of x. That's what I'm talking about, the range. But when I'm talking about the codomain, I'm just talking about the set. All together? Okay, good. So now what we have there, we have got inside here something called the range of f. Now, in other words, in a way, we've got the have a range f within y here. So now, what do I want to talk about today? I want to talk about what we call composite function. What am I talking about? Please note that with numbers, if I've got 2 and 3, there are a lot of things I can do with 2 and 3. What can I do? I can add them and get 5. I can multiply them and get 6. I can find the difference between them in whichever order. Maybe I can get 1 or minus 1, depending how did I take them. So now I can make the numbers interact with themselves to produce another number. So now when I'm coming to composite functions, we're doing exactly the same. I'm now taking the function as objects or as mathematical entities which can interact between themselves to produce another function. Is that clear? Okay. So we go. Now we have just said that the range of this function is a subset of this y. So we can write that now the range of f is a subset of y. So like I emphasize, not everything in y belongs to the range of f. Altogether. Okay. So now, fine. Let's say now we've got here the range of f sitting there. And then we know that x, which has got a value via this function, the value y will be inside there. Altogether. Okay. Now, having that, there's nothing which says from us we cannot have a function between y and z. We can have a function between y and z. But then, if we have a function between y and z, which passes exactly from here, its domain is the range of f. It passes exactly from within the set, and it takes values to z there, and now this function is g. Obviously, what's going to happen? We're going to have a range of g inside here, altogether. Okay. Now, if you look at that, it looks like if you're running athletics, it will look like a relay. One guy runs 100 meters, gives to another guy, and the other guy runs the final race. That more or less looks like a relay. And you as engineers, again, understanding what we said yesterday about systems, these could be systems. These systems take an output, take it there, and this is take this output and take it to that side. So it will be cascading systems of some sort. But then the question is there any function now which will maybe run from there to there? Obvious, if this g is defined on the range of f, yes, there is such a function, let's call it h. What does h do? H will pick x here. That's how h will act. It will actually, the value of h at x will be the value of g at f of x. If you take into g picks x and put it there, and then g picks that value and put it there. Then we want to look at it as a single function. We look at x, which acts this way. It takes the action of f first on x, then it takes the action of g on f of x. And then that function h here, h is going to be called the composite. That's the composite function. But this action is called the composition. What you're doing there, you're doing the action of composing functions. And the function you get there, you get what we call the composite function. Are there any questions there? Are there any questions? No. If there are no questions, then let's carry on and see what happens here. Let's say we've got a function here, f of x equals to 2x plus 1. That's function f of x. And if you look at this function f of x, actually, the domain is all the real numbers. In other words, it is defined for all real numbers. And the range of this function is again all the real numbers, because a line like this will be given this way. It will cut there at 1 and it will go from there down like that, from this way up to minus infinity, up to minus infinity. In other words, it covers all the real numbers. So that's that. That's one function. So now we know that this function acts from R to R. So in actual, its domain is R, its range is R. So now if we now take another function, let's say G. Again, it's G of x, which is x squared plus 2x. That's another function. Again, this function is defined from R to R. No. This is defined from R to, without the graph, maybe it's not easy to do. We need some more analysis to do that. But I think this is from R to the maybe positive what, positive numbers, something like that. But let's not worry about that now. Let's look at what now. What would be g of f of x? Now it's this new function which we are going to call h of x. What is that going to be? Or is it possible also to have something like f g of x? Maybe let's call that function what? Let's call it j of x. It's another function. Yes, that is possible. In this case, this is possible. Now, then let's try to find this h of x. We want something like this, a rule or a law of formation like this for h of x. And here, we would like something exactly like this, a law of formation for j of x. What do we do? The schematic which I showed you here, you can imagine for that function, that will be r, that will be r, and that will be r, all together, because the functions are acting from r to r. So now when you come here, we want to get this expression. This is what we do. This is what we do. We'll say h, we're looking at h of x. We want to get h of x. H is equal to g of f of x. This is a calculation which everybody is supposed to know how to do by the end of this lesson. So now what happens here now? You're going to say g and then say brackets. Inside there now, we're going to put the expression for f of x, which is going to be 2x plus 1. And then after this now, you are going to perform the action of g. What does the action g says? It says what I'm holding in brackets, I squared, I added to 2 times the same thing altogether. So what's going to happen here is going to be 2 altogether. Listen to me. You see, read what I said here. You must be able to, every function you're looking at, you must be able to read back that action of that function, read it back to yourself, so that you can be able to know what to do altogether. Otherwise, you're not going to do it. So, squaring this, we're going to get 4x squared plus 4x plus 1. Altogether. Okay. Those people don't understand why I'm not, what am I doing here? We'll check them later. Right? Okay. Plus 4x plus 2. And then this is equals to 4x squared plus 8x plus 3. That is that function. All together. Okay. Let's immediately do this one together. Let's immediately do this one. Let's say j of x. J of x is f, then g of x. What is f? What is g of x? G of x is x squared plus 2x and that. Then this is equals to what? This is, we get the action of f now, which is going to say 2. This is said, we said yesterday, this is an argument of the function altogether. So then f says, to my argument, I multiply my argument by 2 and then add 1. So it's going to be 2x squared plus 2x equals to, I remove the brackets, then this is what? 2x squared plus 4x. All together. Plus what? Plus 2. No. As you can see here, when we're dealing with numbers, 2 times x times 3 is equals to 3 times 2. And we say it's commutative. Same thing applies when we're multiplying. But that doesn't happen when we're dividing. So similarly, when you look at these two functions here, this one and this one, just take one. Evaluate 1 here. You're going to get 4 plus 8 plus 3, which is 11 plus 3, which will be 15. Take 1 here. It's going to be 4 plus 36, which is saying that these two functions, as they are seen here, this way and that way, they're not necessarily equal. Altogether, I say they're not necessarily equal. But what I'm trying to suggest with that, I'm trying to say sometimes they can be equal, but let's wait, hold on and see. When are they going to be equal? We'll see that later. Altogether, that is composing functions. Questions there? Can I please have questions? Yes?
The composite function g of x, you missed plus 1 at the end.
Oh, I missed plus 1. Or the f of x is stated plus 1. Okay, plus 1. So if I put 1 here, it's going to be 6 plus 1, which will be 7. If I put 1 there, I'm going to get 15. Altogether. Okay, thank you for that. Thank you. Yeah, please watch what I'm writing here, because I might carry it away out by explaining things and writing something different. Yes, another question? Plus 2 again. We're here. Where plus 2? No, I don't think you're reading this thing properly. Read what this thing is saying. F, whatever f is holding, it must be multiplied by 2. And that is multiplied by 2 up to here. Altogether. And then after multiplying by 2, a 1 must be added. That's what it is. Yeah. Still be careful in reading that thing. Very, very careful. Altogether. So yes. No. Tell me exactly what you're missing. Come again?
Yeah.
Here.
Yeah.
You didn't get this. Right. Let's look at G. Look what this I said. This is, how do I read this thing? I say G after F, or G pick F of X. So whatever G picks is here. Whatever G picks, it is squared, then it's multiplied by 2. Do you understand that? So now, fortunately here, G has picked 2x plus 1. So it is squared here, and then it's multiplied by 2. The rest is algebra, which I'm saying you must know how to do it. All together? Okay. Another question? Clarification? But please, when I'm teaching, don't let me go too many steps ahead when there's a point where you don't understand. Stop me exactly at that point. That will be very, very economic and whatever, profitable. Now, are we together there? Okay. So now what did I do? I did all these things with you. So now what I want to do now, there's still, I don't know what happens to my machine. You see, this mouse stops somewhere. It's not supposed to do that. Right. I just want to check what you can do with this one. What you can do with this one. Let's say y is equals to 3x minus 1. And this is, let's say this is your f of x. You must understand this thing very well. Why do we always say y is equal to f of x? Because we plot our functions on the system of x's, which is called an xy system of x's altogether. Okay? So now, these values here, like we said yesterday, the x's is the independent variable. So we can just pick and choose within the domain of the function and they get the value for y. But now if you want to plot the function, the curve itself, you must always have pairs like this, pairs x, y. But if these pairs are pairs for a certain function, this pair is exactly equals to x, comma, f of x. Because it says here, your y coordinate is given by the function f of x. Altogether. Then we can plot the function. Altogether. So that's why we consider y is equal to f of x, y is equal to g of x, and so on and so forth. So now, let's say now y is equals to 1 over x plus 2. And this is our g of x. On your down there, can you please try to find h of x, which is g after f of x? You see the way I've written here, the way it's written here, I wrote g first, and then I got f, but I'm writing it as g after f. Why am I writing that as g after f? You must go to the schematic here. To this schematic here. Is f, then is g, altogether. So when I'm saying g after f, you must have this picture in your system. Okay. So now let's get this. Please push the pen against the paper. Push your pen against the paper. I'll use again h here, but I'm going to now use h, which is f after g of x. So it's y is equal to h after g of x. Can you please find the two again? Just try to practice that and see that you get something correct. It should be easy and quick how to do this thing. Right, who wants to give me his answer for this one? His or her answer. Yes, ma'am. 1 over? You got 1 over 3x plus 2 plus 1. Are you sure you got that, everybody? How did you get that? Let's just check how you got that. The function f is this one, is it? And the g is that one, is it? So when we get g, we'll just say 1 over, the argument is x. Now here the argument is f of x. We must take that 3x minus 1. That is what is replacing our argument altogether. And then plus what? Plus 2. Then you can see here that will remain, if you remove the brackets, we're going to have a 2 minus 1, which takes us there. That is correct. Altogether. Good. That is correct. This side, what are we going to get here? Volunteer? Yes? We're getting what? 1 minus x. Let's check that. F, whatever f picks, it multiplies by 3. So 3 times g, which is that, isn't it? Which is 1 over x plus 2. Close the brackets. We're here. Altogether. Sorry, where are we? We're here, isn't it? Then we've got to carry out this one, which is minus 1. So what this is going to give us, 3 over x plus 2 minus 1. That is what we've got. If you look at these two functions, they're very, very different. Again here, maybe you can do what we did yesterday, try to find the domain of this function and the domain of that function, the range and so on. Altogether? Good. I think at that point, I can say composition of function has been done. Altogether? Okay. So now, let's come to something else. What are we going to talk about there? We're going to talk about an inverse function. An inverse function. I think the word inverse, you've heard it before. Things like additive inverse, multiplicative inverse. You've heard that, isn't it? Have you ever heard something like additive inverse? No? Multiplicative inverse? No. Good. That is very good. That is very good. If you never heard of that, that's fine. Then I'm going to teach you myself. All together? Okay. Now, let's just to get this word inverse into our systems. Let's get it this way. Have you ever realized that if I've got a number x, I can always find another number y. I'm talking about real number in this case. In such a way that when I add these two numbers, I'm going to get a 0. Is that true for all numbers? I get a number, I can always find another number. When I add them, I get 0. It's true. Give me an example. Example of your own number. 1 plus a negative 1. Then I can always get a 0. This is a very important thing, because if you don't know how these things work this way, then you cannot even solve equations. The reasons why we can solve equations is because these things work this way. And then the other one, where does this help us to solve equation? If we had an equation like x minus 2 equals to 7, how would you find x? Is to use this principle. When you want to find x, you want to leave x alone. But leaving x alone is writing x plus 0. That is x. When x is standing alone, it's just as good as x plus 0, isn't it? So now, I want to see here. I want to leave x alone. How can I create a 0 here? So that I can have x plus 0. So what I'm going to do, I'm going to use exactly this principle, that for every number, like a big number minus 2, I have another number, which in this case is going to be a plus 2. I'm just emphasizing the sign there. That is a plus 2. Then these 2 are going to give me 0. But the law of equations says whatever you do on one side, you must do on the other side, isn't it? Then you get that thing as 7 plus 2. Then what you're going to have here? You're going to have a 0. But to have a 0 with x is to have x. Then you get that your x here is equal to 9. Do you see how beautiful is that? It really looks beautiful to me. How does it look to you? Yeah. Then in that case here, when this happens, we'll say minus 1 is an additive inverse to 1. And the 1 is an additive inverse to minus 1. They are like cousins. If you're my cousin, I point to you and say cousin. And what do you say to me? Cousin. All together. So they are additive inverses. All together. So you see, in numbers also they are cousins. Isn't that beautiful? It looks beautiful to me. Then, if I were to solve an equation like this, 2x equals to 8, I need another type of an inverse. But what is it to solve an equation like this? It's to leave x as alone. But to leave x alone here is good as having one x, which you normally don't write that way, but we must understand that when we're having x, we've got one x altogether. So which means to have x here solved, I must have 1 here. So the question is there any way I can create a 1 from a number given? Yes. If I give a number which is not equal to 0, if I've given a number which is not equal to 0, let's say like 2, I can find another number. This number is not equal to 0. I can find another number, in this case, such a way that I multiply it by 2, I get 1. And that number exists, is what? It's 1 over 2. It's also not equal to 0. When I multiply the 2 is that. So that's what when I'm going to do. I'm going now to multiply this equation by half this side and multiply by half this side. But remember, multiplying by a number is a synonym to dividing by its reciprocal. Altogether. Okay. So now you have got that inverse story sitting now, isn't it? So now half is going to be called a multiplicative inverse to 2, and the 2 is a multiplicative inverse to that one. So it's another type of cousins. All together. Okay. Now, let's come back to this idea of inverse function. Of course, here what you're doing, you will, let's say, we start with a function here which goes back to there, which is called there, and they call it f. And always here, again, what's going to happen here? There will be a range of f. All together. Okay. So now we can define a function from within here, which goes back this side. And that function we call a g. But it doesn't mean necessarily that it's an inverse of f. We're not going to call g an inverse of f. If g is an inverse of f, we are going to say g is equals to f. If you've got a scientific calculator, I think you've seen sine and a sine with a power like this, almost in the adjacent patterns or on the surface of the the calculator and the one on the button. It's meaning that this button or key works for sine and works for sine power minus 1. But power minus 1 is not an ordinary power of powering with numbers. It's an inverse. Altogether. Okay. So now that is that. Now, what would this function do if that function does exist as an inverse? This function, if we pick x here, it will take to y then, which is actually equals to f of x. Altogether. So now, if this function g now picks this y, what are we doing? We're saying g of f of x, which is the same thing. If it's an inverse, it's going to be g f of x. Normally I'm going to read this thing this way. I'm going to say f second function. So I write it like this, but I read it as f second function. Let's write it there. We read this as f second function. Altogether. Then this, if we do this, and that is an inverse of that function, this must take us back to x. Now what happens? It looks like we started with x, we're landing at x. Something which, apart from x and land to x, is a special function. And that function, we call it identity function. Now it will be identity function at x. Do you hear what I'm saying? You follow what I'm saying? Let's look at this here. I said if this function is an inverse of this one, what will happen? I will take f via this function, second function, and I'll get back to x. Because remember, this is y, it's here. So if I do the inverse, it must take us back exactly to where we came from. The only way where we came from to get to y, it was at x altogether. So, but I'm saying now, if we start from here, it will look like we started at x, we're ending at x. It looks like it's this function which takes x to x, x to x. And that function called, it takes x to x, we call it identity function. This stands for identity function. What is an identity function? Identity function is the function will take 2 to 2, 3 to 3. Do you know such function? Have you ever seen such a function? No. Yes or no? No. Good. Good that you've never seen it. It's very good that you've never seen such a function. It's very, very nice that you've never seen such a function. So I know all of you, you don't come from schools in Africa or Europe or America. You come from schools out of this planet. So you must be very, very interesting people. You have never seen this function. Y is equal to x. Y is equal to x. That's a function which when I pick one, this is y is equal to x is an f of x. So I pick one, it will give me 1, f of 1 is going to be equals to 1. What has it done? It picked 1, it gave me out 1. It picked 1, it gave me out 1. Pick 2, give me out 2. You get that line which bisect this angle, 45, 45. It comes this side, it bisects this angle, 45, 45. That function is an identity function. It picks x, it gives me x, picks x, give me x, picks x, give me. Now the y coordinate and the coordinate are always equal. You've never seen that line? Okay, you know what happened? You had forgotten. And that is normal. But you mustn't encourage it. All together? Okay. So now you've got an example of an identity function, y is equal to x. It's a good example of an identity function, and you will learn that function from very, very early years in mathematics. Another question. What are we talking about? inverse functions altogether. What is interesting now to me is to say, if I'm given a function like y equals to 2x, I want to take a simple function and plus 1. If I'm given a function like that, how would I find its inverse? Let's say this function is f of x. Does anybody know how to find its inverse? You know? You know how to find its inverse? No, yes. Okay, let's explain it for those who don't know. Now, let's draw the sketches again. F goes this way. Want to find the f inverse which goes this way, or f second function which goes that way. And we've got y here, and we've got x this side. All together. Okay. Now, if you remember what I said yesterday, that a function is an input-output system. All right, right here, system this way is an input-output system. So the input will be here, and the output will be there. Do you agree? Okay. But now, if you look at this kind of situation here, when we get the inverse, it looks like the output has been switched to be input, and the input has been switched to be the output. Do you understand that? These things have swapped around. So now, listen, you might not find somebody, maybe you can talk about this thing exactly the way I'm talking about it now. But I think at the end of the day, we'll arrive exactly at the same kind of understanding. Because at the end of the day, we must have a common shared understanding of exactly the same concept. This is how I do it myself, to exactly express that thing that it looks like the input has been changed to output and output has been changed to input. I do it like this. The input x, the output y. The output now has been changed to input, and the input has been changed to output. This saves me magic. Let's look what I'm going to do now. I'm going to come to the expression here. This expression, I want to find its inverse. I'm going to write. I'll do exactly this. In the place of x, I'll put y. In the place of y, I'll put x. Then I have x equals to 2y plus 1. But functions are plotted on the xy system, xy system of coordinate, and that detects that I must have my functions always expressed as y equals to something. Is everybody at that point? Okay. So now if that is like that, which means now here I must express this as y equals to something. So what do? I go back to those additive inverse, multiplicative inverse. Additive inverse, I need 1 minus 1 on both sides. What am I going to do? I'm going to end up with 2y equals to x minus 1. Multiplicative inverse, I need half. Is it? Then I multiply both sides by half, I get y equals to x over 2 minus altogether. Okay. Now, what are we sitting with now? What are we sitting with? What are we sitting with? We're sitting with y equals to 2x plus 1, and the y equals to x over 2 minus 1. And then, if we now say this is f, this is f. Oh, sorry. Thank you. If you now say this is f, this 2 will be taken to 2 times 2 plus 1. It will end up being 5 here, isn't it? If you now say this is the f second function of x, this is f of x. Now x second function x will take this 5. What will it do now? It will say f second function of 5 equals to 5 over 2 minus 1 over 2, which is 5 halves minus 1 half, which will give us 4 halves, which yesterday this was equal to 2. Today? Still 2. Okay, good. 2. So which means this 5 will be taken to back to 2 by this f second function. So really, this is f inverse of that. Did you see that? Is it beautiful? It looks beautiful to me. But if you don't see the beauty, it doesn't mean that it's not beautiful. It just means that you don't have the eyes to see the beauty. How did I get 5? I don't know. I don't know. I wanted to find out. Pick, there is the rule of formation of the values of f. Pick these 2 and replace it wherever x is and see what you are going to get. Oh, said the blind man sitting at the corner of a round table. Is that all right? Now you know how you got 5. I think you're sleeping for some time somewhere. Sometime. I know people sleep for some time, sometimes. Good. Do you see that? Now, what we're going to do now, I want to take these 2. There are 2 things we've got now. Listen, identity function is very important because now here we have actually seen that the composition of these 2, they give us identity function, isn't it? Okay. But what we've done here, we've done what? We've done f inverse after f. That is what we've done. And we saw that this, using 2, this took us back to 2. Let's say with a 7 here. Then we start with what? With f inverse. If we take a 7 there with f inverse, what is that going to do? Going to be f second function of 7. Which will be what? 7 over 2 minus 1 over 2. And that will be 3 halves, and that will give you 3. Altogether. Then now, let's pick this f second function of 7. If we're picking f second function of 7, we're actually picking 3 altogether. Yes. Then we're getting this as f of 3. Let's see what we get. We go here. 3 times 2 plus 1. 7. Altogether. So what is being said here? It says f pick the second function of x is the same as second function of f after f of x, and that will give us x, which is actually the identity function on x altogether, which means these 2, they actually make us identity function at what is the difference now before with what we saw before? What did you see before? We took f and g, we composed them this way, one direction, and then we changed the order. What happened? They were different. Did you notice that? They were different. In this case, it says, in the case when these 2 functions are inverse, we get exactly the same thing, the identity function. Isn't that beautiful? It looks beautiful to me. It looks beautiful to me. Altogether. So you compose a function and its inverse, you get exactly what you started with, the input which you put in. That's what it said. Altogether. Good. Now what we want to do, what I want to take you to now is to the issues of plotting. We've done this thing, composing functions, isn't it? Now, I think this graph is not going to be very, very important for now, but we've discussed that. What will be interesting now is to see that if we compose 2 functions and we plot the 2 graphs on a system of coordinates, what's going to happen? Then let's take exactly those 2 functions. What are the functions? The functions are y equals to 2x plus 1. And the function y equals to x over 2 minus, is it minus 1? Minus half. Minus half. And then we plot them. Let's plot these functions. This function, the gradient is y2 minus y1 over x2 minus x1, and there is 2 over 1, and the function cuts at 1, which means it's going to be here. All together. And whenever I run 1, I should rise 2. I run 1, I rise 2. Then the line is somewhere here. Do you see that? Okay. Where is it? Where does it cut the y-axis? It cuts the y-axis there. Now, if I really want to draw that line now, what am I going to do? Let's get this. I'm going to say then that line is sitting like that. All together? Okay. Now let's look at this one. Looking at this one, the gradient is half, which means I'll run, making reference to this, I'll run 2 and rise 1. Where does it cut? At minus half. Where is minus half? Oh, it's very small. This is 1, minus half is somewhere there, isn't it? Okay, so let's take it there. Then I'll run 2, 1, 2, then I'll rise 1, then somewhere there. Now if I'm going to draw that line, this is what I'm going to have. I'm going to have a line starting here, going through that point, going through there, and that. Then, which means that line will sit almost this way. Good. Let's change the color of this line. Let's change the color of this line. There is the color is red. All together. Okay. Let's now think of the identity function. I'm asking you to think about the identity function because I want to know where we want to go. Let's now think about identity function. The identity function is y is equal to x. Do you understand that? It's y is equal to x. So let's pick a line here. The y is equal to x line will go this way. And let's change the color of that line again and say, there it is. It's blue. Anyone who wants to look at that line, those lines very, very carefully, very, very carefully, you will notice something. What are you noticing? Come again? They're supposed to be? Yeah, that's what exactly it is. Roughly, yes. If you look at the graph properly, I said it cuts it to half, but then half there is not marked. I just took an approximation of half there. So what do you notice? They intersect one, but there's something more than that. What did you say, my sister? What was it? They are symmetrical around y is equal to x. Altogether, they are symmetrical around y is equal to x. And that is very important. That is very, very important. From today onwards, you must put it in your system squarely seated that if I plot a function and I plot its inverse exactly on the same graph, what I'm going to get a symmetrical kind of body around y is equal to x. Am I making sense? Okay. I think you saw this thing right at the beginning of the lecture. You should have seen this thing exactly right at the beginning of the lecture. There it is. There. That blue graph and the red graph are symmetrical around the dotted line, which is y is equal to x. All together? Okay, so you see, I kept knowing what I wanted to teach. Isn't that beautiful? Look at the graph like that one, which is very, very beautiful graph. Something like that, you can even maybe take a graph which forms, like if you take a graph of the function like, or maybe you don't know this function, but maybe just, do you know the graph of a logarithm function? Logarithm function, do you know it? You don't know it. You'll see it later. We're going to talk about that. You'll see what kind of a beautiful shape you get. You get a shape like a vase, symmetrical like a vase, because of that kind of a thing. So guys, that's where we are now. We now have learned that the graph of a function and that of its inverse, they form a symmetrical body around the line y is equals to x. Now, I think I'm going to stop there for today, but what am I going to ask you to do? You must now get your textbook or your notes and play around with exercises of composing functions. Play around with exercises of finding inverse of functions, composing functions and their inverses, and then see what, including what we did yesterday, the domains and codomains. All together? Okay. Otherwise, for now, I'm going to say thank you for listening. My name is Charles Sugasfani Msipa.